In this video we give a quick intro to post-hoc testing using the emmeans package. Post-hoc tests are hypothesis tests that you didn't plan at the start of an analysis. So an example would be this cortisol problem that we've been looking at. At the start of the analysis we were comparing log cortisol values across three populations, and our null hypothesis is that on average the cortisol doesn't depend on the population. And we saw evidence from an analysis that we can reject that null hypothesis. So there's evidence that there are differences between the populations. So a question that emerges from that is, where do these differences lie? And that's a question we hadn't planned at the start, so we need to do post-hoc testing if we want to investigate that question. One way to investigate that would be to compare pairs of populations, and there are three comparisons that we could make looking at pairs of populations. 1 versus 2, population 2 versus 3, and population 1 versus 3. The problem with doing that would be that as we increase the number of tests we are making, 3 in this case, we increase the false positive rate. So one test has a false positive rate of 5%, which is the critical significance level. 2 tests would increase the false positive rate up to 10%. 3 tests has a false positive rate getting up to 15%. So to do post-hoc testing, we commonly have to correct for the number of tests that we're doing. So that's called correcting for multiple comparisons. And emmeans does that automatically for you, which is one reason for using the emmeans package. So to use the emmeans package, we load up the package, which we've done up here. And then the first thing to do is to create an emmeans object. So use the emmeans function, and you give it a fitted model that you're going to make estimates from. And then you tell it what explanatory variable do you want to make comparisons over. In this case we want to make comparisons over the variable population. So I've called the output from that an object m_eff. And then to do post-hoc testing, we put that into the function contrast. So we give contrast the emmeans object, and then we tell it what comparisons we want to do. In this case we want to do all pairwise comparisons. So the method we're going to use is called pairwise, and that will automatically correct for the number of tests using a method called tucky. So we save the output of that command to an object called m_tucky. So let's run that command. And then we can display the results in 3 ways. The first way is to display all the hypothesis tests with p-values. And before we go into the details, let's look at the bottom here. It tells us that it's adjusted these p-values using Tucky's method, and it's adjusted them because there are 3 estimates that we're making. So that's the correction for multiple comparisons. Now the output, let's look at the first line of output here. This is comparing population 1 to population 2. The estimate is the estimated difference in log cortisol between those two. So population 2 is 0.14 higher than population 1. And then to test that versus a null hypothesis of no difference, it's doing a t-test here and correcting for the 3 tests. So the final p-value is about 11%. So that's greater than 5%, so we can't reject the null hypothesis. So we can't say there's evidence of a difference between population 1 and 2. So just scanning down these p-values, the only one that is below 5% is the comparison between populations 1 and 3. So we can say that we have some evidence that population 3 is higher than population 1. Another way of reporting the same thing would be to look at 95% confidence intervals, and we can use the confint command to produce these. And the way to interpret these would be to look at the upper and lower confidence levels and to see whether 0 is in between those. So if it is, we can't reject the null hypothesis and there's no evidence of any difference. So there's only one comparison where 0 isn't within the confidence interval, and that's the same comparison between populations 1 and 3. You see both confidence levels are negative. So that's giving us evidence that there's a difference between those 2 populations. And the final way to look at this would be to plot up those confidence intervals on a graph. And here the dots are the estimates of the difference, and the blue bars are the 95% confidence intervals. And again, we're comparing these intervals to 0, so the 0 point here is on the right hand side, and the only confidence interval that doesn't cross 0 is this same comparison here between populations 1 and 3. So that's 3 ways of looking at the output of post hoc testing using the emmeans package.